In the last video, we saw people's income in the McDonald's store, and we learned something about their summary statistics. The question was, what was the average income of somebody visiting a McDonald's store, or what's the median income? But there could be much more than that, which would be informative to your audience. So although we found that from our one variable summary, that the median income of a customer visiting McDonald's was $55,270, it does not mean that all people visiting a McDonald's store would be earning something like that, or something even very close to that. Okay, there could be very much of a variability between individual customers in terms of what they earn, and that is something which is captured by other measures. We call them the measures of dispersion. So if we go to have a look at some of the measures of dispersion, here's a list of them: variance, standard deviation, coefficient of variation, range, and then percentiles and quartiles. Some of them are pretty important for us. For example, you may very frequently come across something called standard deviation, and which crudely gives you a sense of the average variability in your data set. So we're going to learn a little bit about these different measures of dispersion once we have covered the measures of central location, as we did in the previous video. Look at this example: choosing your investments. The annual returns in two stocks, X and Y, for the last 10 years are presented here. So you have two stocks, X and Y, and you see their returns, which are obviously in percentages, also given by their side. So now let's say we assume that the past data is a good indicator of what's going to happen in the future. Which stock would you put your money for short-term investment? Now, people may just look at this data set and think, well, I don't know, some years have been very good. For example, for stock X, some years they have returned 9% or 8%, but some are really bad years, like 2%, and one particular year, it was 0%. That means there was no return on that year. Whereas for Y, the returns have not been very spectacular, but there have been plenty of 6s and 5s here. The highest was 7%, but the returns never went below 4%. So which is the choice you should actually make? Given what we have learned in central location, the first thing for us is to try to measure the average returns for both these investments. Okay, so that's if you do the first thing, that is measuring average returns. So if we look at this investment choice, the first thing for us is to try to measure the average returns of these two investments. And if you look at the average for both X and Y, you will see that it's 5.3% return for both of them. So based on the averages, it's very difficult to make a choice. But obviously, there's more to choosing an investment than just looking at the average return. And what people look at when making investment is obviously the risk of the investment as well. While the returns on average are 5.3% for both these choices, the risk is not exactly the same. And as you can see, there's quite a bit of dispersion of returns from the mean return of 5.3% in both cases. With stock returns for stock X, you can see the returns can actually vary between 0% and 9%, whereas for stock Y, they vary between only 4% and 7%. Okay, so obviously it looks that the dispersion is quite different. So how do we actually measure the dispersion? While quantifying the dispersion, we actually measure the distance of each of those returns from the mean return, and that's something is done by Excel or StatTools. So you don't need to worry about measuring individual dispersions. But what we actually need is a sense of the dispersion, and this is what actually is done when computing dispersion, taking the dispersions of or variation of the individual returns from the mean return, and then we all put them together. And in this case, for stock X, we measure the dispersions for individual returns from the mean. You see the difference of 5.3 from all the individual returns, like 0 or 2 or 5%. And then we aggregate them into some measure, which is called the variance. And that's give us a sense of the risk. And you can see that stock X has a higher dispersion than stock Y, as we saw in the picture before. And then we can make a choice that given the average return is same for stock X and stock Y, and the risk of stock X is pretty high compared to stock Y. So a risk-averse investor may prefer stock Y over choosing stock X. Now, the best measure we use for measuring dispersion is called standard deviation. Standard deviation is basically, again, the square root of the variance, which was measured in the previous slide. And the usefulness of using standard deviation is it gives you the numbers in the same units as your original data. So for example, the original data give you returns in percentages. Standard deviations gives you also a sense of the dispersion in terms of percentage. For example, stock X has a standard deviation of 2.67%, while stock Y has a standard deviation of 0.95%. So obviously, stock Y has a lower dispersion than stock X and can be seen as less risky. So a very crude interpretation is returns are on average 2.67% off from the mean return of 5.3%. Okay, so it can cut both ways. So sometimes you may get returns which are pretty higher than the mean, or you may get returns which are quite smaller than the mean as well for stock X. Whereas for stock Y, the returns are more likely to be closer to the mean return of 5.3% in most cases. So that's a sense of standard deviation. The next one we cover is coefficient of variation. Now, why we need to calculate this coefficient of variation? Well, it's not as common to use a coefficient of variation. As I said, standard deviation is the most popular measure of capturing dispersion. But in certain cases where the means of the two investments are, like in the example we saw, was the same, but in some cases it could be quite different. We may be comparing two things which are very, very different and have very, very different central location as well. In that case, the coefficient of variation could be a more useful measure than just simply looking at the standard deviation itself. Now, one example would be this annual CEO salaries in Indonesia and Australia. And again, you can calculate the average, and you can also calculate the standard deviation. The calculation has been done for you here. The average salary for Australia is $108,000, and for Indonesia is $78,000, let's say, for CEOs. Whereas Australia also has a higher dispersion of $81,270 compared to Indonesia's $70,863. Now, apparently, it may seem that Australia has a higher dispersion, but some people may argue that Australian mean salaries are much, much higher than Indonesia. Therefore, we may not be actually comparing apples to apples when we look at the dispersion here of 81,000 and 70,000 for Australia and Indonesia, respectively. So actually, the standard deviation for Australian CEO salaries is only 75% of their mean salary, which is lower than the dispersion for Indonesia, where the dispersion accounts for almost 90% of their average salary. So there must be more inequity in salaries in Indonesia than Australia. Although, if you look at just the absolute numbers, Australia seems to have a higher dispersion. So in this case, this number, which compares or converts the dispersion or standard deviation into a percentage of the mean, and compare that percentage, is called coefficient of variation. Okay, so it is basically expressing the standard deviation as a percentage of the mean salary in this case. Let's look at one more example here. Here again, we are looking at distribution of marks in two schools, what students have got. Okay, so we take 10 students in school A and 10 students in school B. However, in school A, the exam, they mark it out of 10, and people have got marks ranging from 0 to 9. You can see there are 3 people in school A who got a 5 or 2 got a 6. As opposed to school B, where the distribution looks very much the same, but here the full marks are 20. So some people have got even more than 10. You can see that 12, 14, 16, or 18. So in this case, it's not fair to compare the standard deviation, because the standard deviation or the variation would obviously be more in school A2 compared to A1, simply because they have a higher range of marks to offer. So in this case, obviously, we have a lower standard deviation, 2.67 in school, the first school, and 5.34 in the second school, because of the higher marks, higher possible marks they're awarding. So if you're trying to compare the dispersion of the two schools, they're quite the same, and it will be important for us to just look at not the standard deviation, but to convert the standard deviation as a percentage of the mean, which is 5.3 in this case, and get a result. If you compute these numbers, you will see they're exactly the same, about 50%, okay? So the dispersion of the two schools are exactly the same as we see in the picture. So although standard deviation tells us a different story, that's simply because we are comparing apples to oranges here, two schools which are having two different set of marking scheme, and here to make the comparison fair, we need to convert that as a percentage of the mean and compute what is called the coefficient of variation. So it has some use as well for our work. The other ways of expressing dispersion could be percentiles. Percentiles is something you will often come across, for example, in standardized tests like GMAT. They award you not a percentage of marks, but they tell you what's the percentile. For example, if somebody has got a 95th percentile score in an exam, that simply means that they have got more than, or he or she has got more than 95% of the students who appeared in that exam. Or in other words, he or she is in the top 5% of students. Okay, so percentile is another way of describing what your a particular number's position is in the whole distribution. You can see the 10th percentile or the 70th percentile in this distribution of marks in a particular school is indicated here. Okay, the most common percentiles have some name, and they're called quartiles. For example, the 25th percentile is called the first quartile for obvious reasons. So if I say the 25th percentile income in Australia is $30,000, that would mean that 25% of the people are earning below $30,000. Or in other words, 75% of people are earning more than $30,000. And similarly, we have the 75th percentile, a special name called the third quartile. Okay, and then similarly, the 50th percentile would be the second quartile. But as you may have already guessed by now, the 50th percentile is already known by the name median, because the median is exactly the central point in the data. So the median is the 50th percentile or the second quartile of a data set. Going further with quartiles, we have some other measures like range. Range is obviously the range of the data. So when we say the returns can be between 0% and 9%. So we are referring to the minimum point in the data, which is 0%, and 9% is the maximum. So the range is the difference between the minimum and the maximum in a data set. Obviously, the range does not consider other things. It just looks at the minimum and the maximum, the 2 points, to describe dispersion in a data set. It does not tell you what exactly is going on in the middle of the data set, okay? So only the extreme values are considered. Similarly, you have something called the interquartile range. which is basically the difference between the first quartile and the third quartile. So it also gives you a range, but it gives you the range between data points which are not located at the extreme end of the data, but somewhere which it captures the middle range of observations in a data set. So interquartile range is less extreme than range. It tells us what's happening in the middle half of the data set. And I've provided some examples here of interquartile ranges as well, when you identify which is the first quartile and third quartile and see what the difference is between them. All right, and so finally we move on to shapes of the distribution. Shapes, we saw Age of CEO's example before, and as you can see, when we organize them in the form of a histogram, the shape is not really very symmetric. You can see that we have a longer tail towards the right-hand side of the distribution. So these are called skewed distributions, okay? So you may come across distributions which are not exactly symmetric, but skewed in real life as well, okay? So, so skewness is a feature of distributions as well. If a distribution is perfectly symmetric, the mean, the median, and the mode will all coincide. So in this example, you have a perfectly symmetric distribution, and we don't have any skewness in such distributions. We will know that a normal distribution is a symmetric distribution, which we will cover in one of our future videos. And distribution of IQ in the population, for example, can be represented roughly in the form of a bell curve, very symmetric. And you can see the mean and the median and the mode will coincide there. However, in some cases, you will find some distributions which are skewed to the right. For example, distribution of income of people in a country or in a state. It's very likely that you'll come across a distribution which is skewed because some people will be earning extremely high income. Okay, there are few in numbers, but there'll be few of them at the extreme right end. So your tail will be dragged towards the right. So that will basically lift up the average, and but the median of course would be unchanged, and sorry, the mode will be unchanged, and the mean and the median will be slightly pulled towards right if we have more observations towards the extreme right end. So, but the mean would be affected more than the median. So in this case of skewed distribution, you will see that the mean is always higher than the median. So this is, for example, a distribution which is skewed towards the right, and the average of the mean is higher than the median. And on the left-hand side, again, you see a different kind of skew where the mean is basically below the median. So skewness is something which defines the shape of the distribution as well. Let's look quickly at an example of McDonald's, which we completed earlier in terms of its descriptive statistics. And when we look at the McDonald's example and we look at the one variable summary, which we completed in the previous video, one variable summary of income, we saw apart from mean and median, there are lots of information. So you can see the standard deviation is mentioned as $15,000 or $15,550. It also gives you a sense of the quartiles. So 47,000, for example, was the first quartile of the distribution. That means 25% of the visitors to the store earn below $47,000. And the third quartile was $65,000. That means 75% of their customers earned less than $65,000. And similarly, you have the different percentiles mentioned here. If anybody's interested in the 95th percentile or the 5th percentile, for example, which represents $30,000 in this case. So that means 5% of their customers earn less than $30,000. In this particular case. The range is mentioned there, the minimum and maximum is mentioned there as well. So minimum earning income of a customer was $20,000 in the data set, maximum was $94,000. And obviously the range is the difference between the minimum and the maximum which was 74,000. So all these different measures of dispersion are also available under the same menu in StatTools. So you just have to use the summary statistics function in StatTools to understand the descriptive stats, the measures of central location, as well as the measures of dispersion within a variable in the data set. Thank you.